In this problem, we want to find all pairs of prime numbers pq such that pq is divisible by 5 to the power of p minus 2 to the power of p times 5 to the power of q minus 2 to the power of q. So, our key tool is going to be the Fermat's little theorem for number theory. It says that Fermat's little theorem states that a to the power of x is going to be congruent to a mod x for a prime number x. Applying this, we have if p is divisible by 5 to the power of p minus 2 to the power of p, then we have 5 to the power of p minus 2 to the power of p is congruent to 5 minus 2 congruent to 3 mod p. And then for p is a factor of 5 to the power of p minus 2 to the power of p, we need 3 is congruent to 0 mod p. So this means that since p is a prime number, we have p equals to 3. With the same logic applied to q, we have q equals to 3. So 3 is going to be one of the solutions. And then first, let's set p equals to 3. Our condition will become 3q, case 1 is p equals to 3. So then we have 3q is going to be a factor of 5 cubed minus 2 cubed times 5 to the power of q minus 2 to the power of q. So 3q is going to be a factor of 117 times 5 to the power of q minus 2 to the power of q. Since 117 equals to 3 squared times 13, we have 3q is a factor of 3 squared times 13 times 5 to the power of q minus 2 to the power of q. Divided by 3 on both sides, we get q is going to be a factor of 3 times 13 times 5 to the power of q minus 2 to the power of q. And then this implies two possibilities for q. Q is a factor of 5 to the power of q minus 2 to the power of q. From step 1, this means that q equals to 3. Or q is a factor of 3 times 13. Since q is prime, q equals to 3 or q equals to 13. q equals to 3 is already covered. So we have q equals to 3 or q equals to 13. The second case is q equals to 3. By symmetry, since this problem is symmetrical, we have if q equals to 3, by the same logic as the first case, we have p equals to 13. So our answer choices would then be 3, 3, 3, 13, and 13, 3. So that is how you solve this problem.